The paper of the day is Dictionary-Based Order Preserving String Compression for Main Memory Column Stores. It's a 2009 paper. This paper shows an approach for efficiently using dictionaries for compressing a large set of variable length string values with fixed length integer keys in column stores. The dictionary supports updates without changing codes for existing values in many cases. Furthermore, they have presented a new approach for indexing such a dictionary that compresses the dictionary itself while offering efficient access paths for encoding and decoding. Authors also discussed a concrete leaf structure and new cache-conscious indexes that can leverage the shared leaves indexing approach. In order to generate meaningful workloads, they implemented a string data generator that allows us to tune different parameters like the number of strings, string length, alphabet size, the distribution, and others. Paper did not use the TPCH data generator dbgen, for example, because most string attributes either follow a certain pattern. For example, the customer name is composed of the prefix customer and a unique number, or the domain size of such attributes is too low. Authors executed 3 experiments. The first experiment shows the efficiency of the leaf structure and compares it to the other read-optimized indexes. The second experiment examines the 2 new cache-conscious indexes using different workloads. And finally, the last experiment shows the overall performance and scalability of the approach. Now, looking at the contributions of the paper, there are 4. First, a new approach for indexing a dictionary of string values that leverages an order-preserving encoding scheme efficiently. In the shared leaves approach, indexes on different attributes can share the same leaves in order to reduce the memory consumption while still providing access paths. Second, a concrete leaf structure for the shared leaves approach that can be used by the indexes of a dictionary for efficiently encoding and decoding string values while the leaf structure itself is compressed. We also discuss the most important operations on this leaf structure, that is lookup and update, and analyze their costs. Third, as another contribution, they present 2 new cache-conscious string indexes that can be used on top of the leaf structure to efficiently support the encoding of the string data in dictionary. For the decoding of integer codes, they argue why the CSS tree is optimal. Finally, the experiments evaluate the new leaf structure and the new cache-conscious indexes under different types of workloads and show a detailed analysis of their performance and their memory behavior. As one result, the experiments show that in terms of performance, the leaf structure is as efficient as the other read-optimized indexes while using less memory. That is primarily due to compression. Now let's give this paper a PS score. Overall, it's bumpy read due to its code, so it gets 6 out of 10 on readability. With 13 pages, it scores 8 out of 10 on length. Reproducibility shouldn't be too challenging, so it gets 7 out of 10. Industry value and learning meter is decent, so it gets 7 out of 10 on each. Overall PS score is 7 out of 10.